This is lecture 6A for Calculus 2. It's the area between curves for competing functions. In this case, we're calling it the area between curves, but we do, it's okay that the result is negative. It has meaning for the problem. So there are two examples that come to mind where this this area between the curves can be negative and have meaning, and one is when you have the velocities of two objects or two particles or two vehicles, and you are looking at the relative distance between those, whether one's in the lead or the other one is in the lead. And the other, and this is one of the homework problems, is when you're looking at the marginal cost and the marginal revenue. If the area between those curves is negative, the profit is negative. If the area between the curves is positive, then then you do have a gain, right? And where they cross, where the profit is zero, is the break-even point. All right. But we're going to do the example here for the distance between two vehicles. So what we have here is some function that's the velocity of one vehicle, and g is the velocity of another vehicle. Recall, if I integrate velocity, I get position. So what I'm doing here is I'm integrating velocity 2 minus velocity 1, or 1 versus 2, and what I'm going to get is relative position. I'm going to get the location of 2, in this case, minus the location of 1. Right. If the location of 2 is less than the location of 1, that means 1's in the lead. Okay, and that answer would be negative. If I get location, and vice versa, it would be positive if 2 is in the lead. So we'll see that in a second. Okay, so when I integrate here, I'm getting the difference between the positions, therefore the distance between the two vehicles, and I can tolerate negative or positive. I don't want this absolute value sign. Remember that when we did the area between curves in the other lectures, we really wanted the area between the curves. In that case, we put, all right, we put the absolute value sign on this, and it would always be so that this would be greater than or equal to 0 because we were expecting a physical area. Here it's not a physical area. We want the distance between the two vehicles, and it's negative or positive depending on who's in the lead. So here's an example. Let's say we have a car, and that the velocity function of the car looks like this. Car at t equals 0 is already going 75 something or others, maybe miles per hour, I suppose, if it's a car. The plane, the velocity of the plane is given as t squared. So initially the plane has a velocity of 0. It's not moving, but the car is moving, and we're going to have a race between these two vehicles. And what we're looking at is the distance between the car and the plane. So that's the definite integral from 0 to t, I'll let t be arbitrary here, of the velocity of the car minus the velocity of the plane. Now notice I didn't put the tau here. The independent variable is t, but if I integrate from 0 to t, then under the integral sign I will have to do, I just put f, I need to have the dummy variable under the integral sign cannot be the same as a limit of integration. That just doesn't make sense. So if I'm integrating with respect to time, I can replace all of the variables of time under the integral sign with another variable. These, of course, get integrated out, and they're only dummy variables, placeholders, so it doesn't matter. But it does matter that they cannot be the same as one of the limits of integration, if that limit happens to be a variable. So here, that's why tau is used here. Right. So, of course, I can just carry this out. This will just be the power rule. But let's look at what it means. Okay, in this graph, we have the velocity of the car and the velocity of the plane. Here is the car. Here is the velocity of the plane in red. And these are velocities. Okay. When I integrate, I'm getting the area between these curves. Now, as long as the velocity of the car is greater than the velocity of the plane, you can see that this whole integral is positive. Okay, and the reason for that is that the car is in the lead. Now, you might think, oh, they cross here, and now the car is going to fall behind, but that is not the case. when I'm integrating from 0 to t, then say I go from 0, change color here, 0 over to this point, let's just say here, then I would have the sum of this positive area in here. Here I would have a little itty bit of negative area. The plane is catching up, but it hasn't overtaken the car yet. Same with those revenue and cost functions. The revenue might be catching up, but it hasn't overtaken the cost. Right? So you will not have the car and the plane at exactly the same location until you have the area over here. We'll call this blue area. How'd that happen? Okay. Okay. Let this area be the positive area here, right here. And now we'll let the area over here be the negative area. And in the definite integral, when you're going from 0 up to here, you're including all of these areas as you go along. You're not just looking at this area right here between 10 and, say, 17. You're looking at the whole area from 0 up to 17. So even though the velocities are the same here, the car can still be in the lead until the blue area, which is positive, is equal to the negative red area. So at that point, these two areas cancel each other out, and the car's location is equal to the plane's location. In that case, the integral, I think it's from 0 to about 17, will be 0. So when it's 0, the two vehicles are tied. When it's negative, the first one under the integral sign is in the lead. When it's positive. When it's negative, the second one under the integral sign is in the lead. And what we were doing was integrating velocity of the car minus the velocity of the plane. That's the point I want to show you, though, is thinking about what this definite integral means. When you start at 0 and go all the way up to 17, you would have this positive area. In fact, you could break it right here and make it two integrals. You have this positive area, then you would have an area that's negative. And when those two have finally balanced each other out, the car and plane are tied. When this exceeds the positive area, then the plane is in the lead. So remember that they're tied at about t equal 10. So here's the result of that integral. So what we did is integrate the velocity of the car minus the velocity of the plane, no absolute value signs, from 0 to t d tau. Okay? Car started out, well, there wasn't much of a gap between them. Okay, well, actually there was no gap between them here, but the car had an initial velocity of 75 miles per hour where the plane was stopped, wasn't moving. The car is in the lead, and at this point, look what happens here. The car is still in the lead, but the plane is catching up. So this integral is becoming more and more negative. At about 17, then those two areas between the velocity curves have balanced out, the positive area and the negative area, to the point where the car and the plane have caught up. After that, the plane just takes off and wins the race.